We continue with electrostatics and now focusing on the concept of the electric field, what's called the electric field. We've done something similar in the first semester of physics by calculating weight equals mg. That little g symbol is, in a sense, a field, a gravitational field, and it's easy to calculate the weight of the object if we're given the mass and we know we're on the Earth and can use 9.8 downward for the value of g, the gravitational field. For the electrical case, the field points in more directions. It's not just down. But that's where we're headed here. The usefulness of the electric field is finding force without using Coulomb's law, but the force is equal to Q times the electric field value. Electric field is created by charge. So here's a picture, an illustration with a positive charge here. These blue lines are the electric field lines. And something you could note about the vectors here, the electric vector, it gets smaller as we move away from the charge. We'll talk about the calculation of the magnitude of the electric field later. Also notice that it points away from positive charge. You can deduce the direction of the electric field. Let's say right here we want to know the direction of the electric field. We imagine putting a small positive charge at this location and then observing what's the direction of the force on that charge. Now if we put a small positive charge here, it's going to be repelled by this positive charge here in the middle and gives us a direction off to the left. That's the direction of the electric field. The direction of the electric field follows the direction of the force on a positive particle. And you can imagine putting that positive particle in space, any place around this positive charge. It would be moving away, the force would be away from this positive object here. So the value of the electric field is represented by these vectors. The electric field lines would be just a solid line going out from the charge, and you have to observe a little bit of the spacing. When the spacing of the electric field lines is wider, the electric field is weaker. When the spacing is closer, the electric field is stronger, is the graphical representation shown here. So we have positive charge here. It's really the same as the previous slide. Now a negative charge. And if again we put a positive charge out in space someplace, it would feel an attraction to the negative charge, though the electric field lines point in. Electric field lines start on positive charges. Electric field lines end on negative charges. What do you think the difference is in the two charges here in frame B and frame C? We're seeing more electric field lines. They're closer together. That tells us the electric field is stronger. That instructs us or informs us that there's more negative charge here. A larger charge creates a larger electric field. So widely spaced lines, small amount of charge. Lines close together, strong amount of charge. Lines point always towards the negative charge. The electric field lines are always away from the positive charge. And again, when we know the electric field, if someone would tell us the number of coulombs of the charge and tell us the electric field happens to be 10 newtons per coulomb towards the right, then we could calculate the force. Just multiplying the charge in coulombs times the electric field in units of newtons per coulomb. The direction of the force is the same as the direction of the electric field when this Q is positive. When the Q is negative, the direction of the force will be opposite to the direction of the electric field. We will have the opportunity to use sine and cosine with electric field. The electric field is not always going to be strictly on the y-axis or x-axis. So working out problems, occasionally we will need to find the components of the electric field. So here's an electric field, 1.26 10 to the 5th newtons per coulomb. 63.4 degrees is given here. And we'd use cosine to find the x component of the electric field. My only little quibble here is this should be a negative since it's pointed off to the left, and positive x-axis is usually taken to be positive. And the electric field here, we'd use the sine of 63.4 degrees times the hypotenuse to produce this value of electric field. So that's the electric field, and if we have two electric fields, we'll add them up to find the total electric field. Resolve the vectors. If we're given the x and y components, we can resolve the vector. If we're given the electric field and given the angle, we can find the two components, and again, you'll have opportunity to do both types of calculations. Starting with the hypotenuse and angle, find the components, or given the components, find the net electric field and its angle. Of course, we'd use inverse tangent here to come up with the angle for the electric vector, and you'd have to specify whether it's away from the negative x-axis or away from the y-axis, and using a drawing is always a good idea. If we have multiple charges, then we can get some more interesting behavior and curvature to the electric field lines. Now here we have two positive charges. If you imagine putting a positive charge someplace in space here, it's going to be repelled by both objects, repelled most strongly by the charge it's closest to, and we get these bending of the electric field lines in this representation. And you have to kind of use an active imagination here. Imagine putting positive charge at different places. Would you agree that if I put a positive charge here, it would not feel the electric field line should not be drawn towards this Q2? Yes, because the charges repel. The small charge I put out here is positive. This charge is positive. This charge is positive. So we get pushed away from the center of the drawing here. Now that's electric field lines, and hopefully you'll have some practice in your laboratory with this. Or you should go ahead and in the OpenStax College Physics textbook, there's a link to the PHET, P-H-E-T, simulations for electric field, and you can drag positive and negative charges around on the screen, and you'll get some understanding of the direction of the electric field. So go ahead and try that simulation. This is Colorado PHET, phet.colorado.edu/sims, and you could click on through to find the sim for electrostatics. Some other examples here. Two negative charges give a similar thing, just that the arrows now point towards each negative charge. Or if we have one positive and one negative, now if I put a positive charge out here, it's repelled by this positive, but it's attracted by the negative. When we're closer to the positive charge dominates the force, and the small positive third charge I put out here would move away. But as it gets further away from this charge, the force from this charge becomes more important, and eventually that small positive charge would be drawn down to this negative charge. So this is an electric dipole. Electric dipole. We have equal magnitudes of charge, and they have opposite signs. Electrical forces are crucial in biology for producing certain molecules and how the molecules link together to form structures. We are not going to cover that in this introductory physics course, but it's worth your reading to spend some time there. It is interesting that water is a polar molecule. As the hydrogens sit out here, the charge is not evenly distributed in the water molecule, and we end up with one end of the water molecule being more positive, one end of the molecule being more negative. So that's our situation with water being a polar molecule. And trying to get the slides to advance here, so we'll do that manually. So in a little summary here, here's what we have for this little section on electric field, and we'll do calculations in my class on values of the, well, I'm not going to be able to continue with that slide. I just somehow closed the PowerPoint. But the electric field is equal to force over the test charge, F over Q naught, and force would be equal to electric field times the charge. The electric field is KQ over R squared, very closely related to Coulomb's law, but there's only one Q in the denominator. F equals KQ over R squared. Well, now back in operation with the PowerPoint. Again, electric field has a value calculated by the force on this small charge, positive charge, divided by the magnitude of this small charge. And the direction of electric field and force are the same as long as this Q is a positive charge. And we can switch this around If we know the value of the electric field and we know the value of some charge, we can calculate the force on that charge. Just taking Q times E gives us the force. Force is Coulomb's law force, KQQ over R squared. And if I now divide Coulomb's law by this Q naught, then one of those Q's cancel in Coulomb's law. And a way of calculating the electric field at a particular point would be the electric constant times the charge that's generating the electric field divided by R squared. R is the distance from the charge that's generating the electric field. So this Q is creating the electric field value. It would be the charge at the center. We want to know the electric field at some place, some distance away. KQ over R squared would provide that. So practice with those. Ask your instructor questions on calculating electric field and making drawings of electric field lines.